We start to continue talk about waves. In last class, we talked about internal waves. One particular type of internal wave is the interfacial wave. Interfacial waves. So think about that. The air and the water, there's an interface. And in the ocean, in some cases, for instance, where the thermocline is, there's also act as an interface. So that interface can develop wave, propagate along the interface. And this is a figure I find to show the internal wave, idea of internal waves. So two layers of water have different density, and there can be developed waves along the interface. And one interesting feature is that although the wave is developed, there's not much wave at the surface. So the surface is usually flat at its cases, but it shows some possible slicks. So although the surface is flat, but because the water are converged along this area, so they may form a small surface feature, surface curvature in this case. But most of the time, these waves are big waves in the subsurface. You cannot see from the surface. And one important parameter for internal wave is called the buoyancy frequency. They have another name called I don't know how to pronounce the name, but we usually call it buoyancy frequency. So the buoyant frequency, I will skip the mathematical part for this one. You can look it up if you're interested. But this is the natural frequency existed due to the buoyancy. So think about this way. There are, let me bring this. So there are different density. Here and here, there are different density. And thinking about if this red dot is a water particle, if I bring its equilibrium here, let's suppose at the beginning equilibrium here. But if I bring it down, the buoyancy will push it up. So you'll try to get up. And then up here, the density here not enough for him. So it will fall back again. So you develop this motion. So how fast this wave particle bounce back and forth depends on the density difference between the rho 1 and rho 2. So that's why there's the rho dz. This is a vertical difference, gradient force for that boundary. So basically, this is how it defines. If you have a larger difference, you expect it bounce back and forth much quicker. So it will quickly dissipate the energy and then kind of get back to where it stopped. Think about if the buoyancy frequency is very low. Think about the density difference very, very low. This particle will bounce back and forth very, very slowly. So it will take a long time for it to dissipate energy because the buoyancy force, this difference is too small. So this is kind of a natural frequency. We can also see this happen in the air because there are air stratification. Air, they also have different density layers. They can also see this in the air. So this is the internal wave from the surface, and these surface slick are due to the water converge and diverge at the area. But remember, those waves are mostly biggest part in the subsurface. It's not from the surface, but sometimes we can still see the surface signature for that kind of waves. This is the internal wave soliton using acoustics and showing the internal wave breaking. And when internal wave break, it dissipates a lot of energy. So that energy, breaking energy, will create the turbulence and then maybe help us bring the underwater nutrient up to the surface or distribute the nutrients. So they have a lot of important role the internal wave play, especially when it breaks. And it also kind of related to the heat transport and everything for our climate. So there are a lot of efforts on investigating the internal wave and how it kind of display energy. So that's one big direction of the internal wave research. It's about its energy. And this is an example for internal wave in the atmosphere, which we can see. So in some days, you probably can see that the cloud is not like a big chunk of cloud. It's kind of a form of nicely layered, not nicely layered, this kind of periodically stripes. So this is because the internal wave, the air is moving this way, so kind of divide the cloud to separate them into this shape. So this kind of for you to imagine kind of the, so you can, if you can measure this, you probably can already measure the wave density for the internal waves in the atmosphere. And I have a video for introducing this buoyancy frequency, but it's based on atmosphere. But remember, the same idea also can happen in the ocean. Oops, I didn't play it.
I was going to talk about a thing called the Brunt-Weissala frequency.
You're going to have to do a lot of explaining. A lot of explaining.
Well, first thing to say about it is one of the reasons why I wanted to talk about it is it actually has a symbol. So getting back to 60 symbols roots, for some reason, this particular frequency is always giving the symbol capital N. And actually, I've tried very hard to find out why it's called capital N, and I can't find anyone who would explain why it's called capital N. It's just every textbook you find it in, it's always called capital N.
You'll find out in the comments.
Probably, yes.
All right. What actually is it?
So actually what got me to thinking about this is just the other day I was thinking, I knew you were coming to do some filming, I was thinking, what can I talk about? And I was just glancing up at the sky, and it was one of those days where the clouds were in lines. You know, you sometimes see very neatly arrayed lines of clouds. And I realized that actually there's a really nice simple piece of physics which explains why you sometimes get the clouds in lines like that. You find it particularly if there's a mountain downstream from the mountain, if you've got air blowing over the mountain, you'll find these lines of clouds there. So what's actually happening is, we need to back up a little bit and do a little bit of physics, which is, I need to talk about buoyancy. So if you've got a balloon, a helium-filled balloon, of course it rises because it's less dense than the air around it. And obviously the less dense something is, the faster it rises. And obviously if it's denser than air, it'll sink. And if you've got it exactly right, it's exactly the same average density as the air around it, it'll just float wherever you put it. And if you move it up, it'll stay there. And if you move it down, it'll stay there. So that's a thing called neutral buoyancy, that the thing just basically stays wherever you put it. And that's what will happen if you've got kind of a uniform density atmosphere, that you can take something that's floating there, you move it up, it's still floating. If, on the other hand, you've got a stratified atmosphere, so actually say the density decreases as you go up, as the Earth's atmosphere does, then what will happen is you've got something which is neutrally buoyant at this point. And let's get rid of the balloon, let's just have a little blob of air there. If you were to displace it upwards, suddenly it's surrounded by air that's less dense than it is. And so it'll sink again. And it'll keep sinking, it'll actually sink through its original point, and then it'll find itself in a region where it's less dense than the stuff around it, and now it'll start to rise. And so it'll actually oscillate backwards and forwards. And the frequency at which it oscillates backwards and forwards is this thing called the Brunt-Weissala frequency. And the reason why that has to do with these lines of clouds is that if you have some air with some moisture in it, if it starts undergoing these oscillations, then as it rises, it'll cool, and suddenly it'll cool to the point where clouds condense, and so you actually make clouds, and then when it sinks again, those clouds will then evaporate again, and the clouds will disappear. So if you've got air which is traveling along and undergoing these oscillations, you'll get clouds, then the clouds will disappear, then the clouds will appear again, then the clouds will disappear again. In the atmosphere, the period of this oscillation is something, it's of order 100 seconds, typically, if you look at how the atmosphere is stratified and use all the physical parameters. It works out about 100 seconds. And typically air is traveling at maybe 10 meters per second, normal kind of wind speed. So in each oscillation, it will have traveled about 10 meters per second over 100 seconds, you travel a kilometer. And that's why the scale of these clouds is typically a kilometer or so, that you'll get a cloud, then a gap, then a cloud, and there's typical spacing between them is of order of a kilometer.
So it's just depositing a little cloud at the top of its wave.
It's actually, well, the same air will form the cloud, and then the cloud will disappear again. So you basically create the cloud, and then the cloud disappears, and the cloud appears. So you're sort of seeing those high peaks. When it goes up, it forms the cloud. And it's wherever you're at the top, you get the cloud, and then it disappears again, and then reappears again.
Won't that oscillation fade away? Won't it eventually stop oscillating and just sort of stop, like a pendulum eventually runs out of puff?
if you just look at the maths, you actually can figure out what the maths of this oscillation is. It really is this thing called the harmonic oscillator, and the harmonic oscillator will just keep oscillating forever. Now, obviously, there are other effects going on as well. So there will be damping terms, which means that actually one of these waves won't actually last forever, but it really can persist for many, many oscillations. So actually you can have this whole series of clouds being created in that way. So this frequency comes up all over the place. So it comes up in oceans, because you can have exactly the same effects in oceans of pockets of water rising and falling. In stars, you can have little bits of the star in the stellar atmosphere rising and falling, and they're all driven by this same frequency, this bisolar frequency. On the other side of the solar system. And again.
Okay, so this is a video talk about the buoyancy frequency. So it also occurs in both atmosphere and the ocean. Next, we to talk about a little bit more realistic case. This might blow your mind because it's kind of very complicated to understand, but bear with me for now. We talk about the interfacial internal waves, but in real case, in the real ocean, the ocean is not nicely interfaced. They are continuously stratified. So this is the density profile, vertical density profile, potential density as a function of pressure. And you can see as it goes deeper, we have this nice, quickly changed density gradient. But after that, it's kind of we call it weakly stratify. After that, the density change is not that big; it's a slowly change. So in this case, you may think there is an internal wave propagating around this area because they are kind of nicely separated into different layers. But in some weakly stratified cases, like this part, there may also have internal wave propagating inside this. But slightly more complicated is that these type of internal waves, they're not simply like interfacial wave propagating in this direction. They kind of propagate as an angle. As an example here, oh, sorry about the noise. Let it go. There's a dog in my house. All right, back to where we were. So in this weakly stratified cases, the internal wave may propagate with an angle. Think about that, because now the water is less stratified. If I raise up the water particle, it will bring up some water particle above him. So this kind of motion also propagates along this direction. That's possible. But one of the important reasons that make it propagate as an angle is something called, it's related to the rotation of the Earth. So let's talk about that first so that we can come back. So there's an inertial force happens, you can observe like either in the surface or in the sub-ocean is that there's rotation. Our Earth is keep rotating from west to east, kind of rotating all the time. And think about that. If in the equator, you are not spinning, but in the like high latitude, you like spin very quick. And so think about this. We kind of talked a little bit about this before. Remember the Coriolis force, right? Okay, I think they have figure here. Think about it in the north hemisphere, and if you are going this way, you will keep deflected to your right. Keep deflecting to your right. So as you travel, you kind of you travel this way, but the Coriolis force is to your right, so it will kind of bring you back, and then travel this way, it kind of deflected you this way. So it kind of in a long distance, it forms this nicely circled. And this is called inertial motion, or in the currents, we call it inertial currents. But fundamentally, it's due to the Coriolis force, kind of act as a centrifugal force. And this is the image for like the surface currents they measured. So this is kind of happened on a very long scale. So this is 5 kilometers, and this is, okay, so they talk about hours. This is about 12 hours. So you can see the order kind of have this slow motions. And they call this inertia currents. And this curvature is due to the rotation of the Earth, the Coriolis effect. And for Coriolis effect, they have a natural frequency for that. And that frequency is called Coriolis frequency. And it's defined as this. So this omega is the rotation of the Earth. You can look up the exact number, but it's about like 1 cycle per day. So you can convert that to radian per second mathematically. And this phi here is the latitude, because we know the latitude going to affect our this Coriolis frequency. So this is a definition of Coriolis frequency. For low latitude, you have very low Coriolis frequency, but at high latitude, they can have very big Coriolis frequency there. I think yeah, I think so. Okay. And now we can move to talk about the internal wave in continuous stratified ocean. We have two kinds of frequency. One is called the buoyancy frequency, and that buoyancy frequencies happens in the nicely layered oceans. Depends on the density different. And that's the interfacial internal wave, right? So if this is two different of density, and the wave will propagate along this direction. It will bounce up and down here, and then this is going to propagate in this direction. And right now, think about there are also Coriolis force, Coriolis frequency. So the Coriolis frequency will kind of keep you moving because it's rotating, right? So it kind of have this motion, make you horizontal motion, make you like move a little bit. And you move, you drag the other particle. So the propagation is vertically. Thinking about if you move something on the top, you propagates, you still stir something on the bottom. So it's kind of direction is along vertically. So in reality, the internal wave propagates with a combination of these two frequencies. So so it will kind of eventually it will happen at some angle, and that angle depends on the this Coriolis frequency and also the buoyancy frequency. And did I get the okay? I didn't include a equation for the angle here, but this angle theta, you can it's just defined as this vertical and horizontal frequency, the ratio. So it kind of can propagate along this way or this way, depends on different situation. So this is kind of very, very hard to understand, but this is kind of the way it is. And they already find some evidence for that. Okay, talk about the buoyancy frequency a bit more. This is the profile, density profile, and this is when you calculate the buoyancy, you can calculate from density. So you have a density. What you are looking for is the density, vertical density gradient. So the gradient is probably big here and gets smaller and smaller, smaller. So this is how you get your buoyancy frequency. The buoyancy frequency is big here and gets smaller, smaller, smaller. This is brought as cycle per hour. So along the thermocline, we probably get biggest buoyancy frequency, about 4 or 5 something here. And as you go deep, the buoyancy frequency significantly decrease. So here, if I'm here, I'm bouncing much quicker. If I'm here, the internal will bounce much slowly because I'm less stratified. This is just the idea of buoyancy frequency. So I would expect here the density gradient is much stronger because I'm bouncing very quick. The restoring force is very much stronger. So that's because of the density gradient is stronger. Okay, so you have to connect this figure as this one. Okay, here this is weakly stratified. We can think about this way. The buoyancy frequency at the shallow depths, it's much larger than the deeper depths. So when it travels, you always have the vertical components. That's due to the rotation, the F, that doesn't change along depths. But the horizontal components, it will change, depends on where you are. If you are very close to the surface, you will have very big, this is called buoyancy frequency. But as you go deep, it will get smaller and smaller and smaller. So the vertical components stand out. So that's why it propagates at this weird shape for internal wave at stratified ocean. So it's very hard to understand, but they already observe some angles, like propagating angles like this, and match the theory. But it's still a challenging topic for now. But this is just an idea for that you guys know the the weird thing about internal waves. It can be very interesting. And anyway, finally, we will talk just a little bit about the generation of internal wave. So there are different mechanisms that can generate internal waves. In fact, any mechanism can generate internal wave, as you can somehow disturb the subsurface. So one way is the wind. The wind forcing generate the surface wave, but the surface motion sometimes can penetrate and cause the interface also to move. An important generation of internal waves near the continental area or continental slope. When there is a big continental slope, tidal forcing back and forth will usually disturb the interface, and then generally internal waves start propagating. And also internal waves tend to break or tend to dissipate along the continental slope. Think about if your internal wave traveling here, and you are very likely to encounter some boundary, that's the continental slope, and you have to dissipate energy there. So there's also a lot of interest in studying the internal wave at the continental slope. Not just their generation, also their dissipation. And they dissipate a lot of energy, and that will generate a lot of turbulence in the water and mix the nutrient and all of things. And that's important for ocean. And other parts, they can also have this called lee waves. Usually lee waves or hydraulic jump is something like when there is a bump, it's a seamount or just a small hill. And when the wave propagates, any kind of force, it can be tidal forcing or other things. When there's a current, it has to jump up this hill. It will have to bounce up, and then because if it's bounced up, it's going to be too heavy there. It has to sink once the hill, once he passed the hill. So bounce up and then down, and because of the motion, it probably sink too deep, and they have to go back up again. So this how they generate this internal wave motion at the deep ocean. So there can be a lot of mechanism. Also, eddy can generate internal waves. When the eddy, we talked about that before, it's a big circulation of the water, and when it hits something or just when it loses its energy, that no longer form the eddy anymore, it can develop some internal wave as well. Okay, so that's for internal wave. And after that, we continue to talk about the Coriolis effect, rotation of the Earth on waves. So speaking of the rotation, recall this, in the northern hemisphere, the Coriolis force will always deflect to the right. And in the southern hemisphere, it's deflected to the left. Okay, right now think about this case. If there's a current going this way into the screen, and you are in northern hemisphere, what you would expect is that the water is going to pile up on the right-hand side. And there's an important thing here is on the right-hand side, there's a boundary. So if there's a boundary on the right-hand side and you're propagating into the screen right now, the direction right now is into the screen, and you're going to pile up here. The water shape, the surface is going to look like this, because you try to pile up on the right side, but there's a boundary here. The water nowhere to go, so it pile up here, and this kind of happen all the time. Think about if you're a river, usually the right side of the river is usually deeper than the left side. And that's because of the Coriolis effects as well. Because the water kind of push the right side harder due to the rotation of the Earth. Yeah, I kind of love that. It's interesting but useless knowledge. But anyway, so this is the idea of Coriolis effect. So this will form is if there is a boundary here and you try to pile up on your right-hand side, and the wave amplitude is going to be different. If you are close to the boundary, you will get bigger amplitude. But if you are far away from the boundary, the amplitude will get smaller. So they find this and they call this Kelvin waves. So the Kelvin wave is just regular wave, but at this case, the rotation of the Earth is important. Excuse me. The rotation of the Earth is important. Similarly, if you think about in the other direction, you have propagate in this direction, and there's a boundary on your right-hand side, you can also develop this. And we have a lot of evidence for this. They observe this Kelvin wave. I think I have a video to show you what Kelvin wave looks like, so it's easier for you to imagine. Okay, so this is how it looks like. Let me repeat this. Right now the boundary is here. Think about there is a boundary here. So the water has to pile up at this side, but it has nowhere to go. So the water has to pile up. So the amplitude here is going to be bigger than the amplitude here. So this is the idea of Kelvin wave. And to get Kelvin wave, we need a boundary. And we usually need like low wavelengths, long wavelengths. So it's a kind of low frequency waves, because we need very long wavelengths to guarantee that the rotations start to play a role. If you are very small, like motion, that rotation doesn't affect you much. But if you are propagating a very, very long distance, that rotation effect can be much more significant. And more interestingly is the Kelvin wave also can occurred at the equator. We talk about the Coriolis parameter change, Coriolis effect change direction at the equator, and the equator sometimes can act as a boundary. In this case, we talk about upwelling current. They are upwelling around the equator, and same idea. The Kelvin wave can also develop at the equator. So this is satellite image for sea surface height. We can see along the equator, they usually have like higher amplitudes, higher sea surface amplitude. And why? Those are just current, like the Kelvin waves. So I have an image to explain that. So think about this as equator, and waves are traveling in this direction. And because in the northern hemisphere, you have to pile up on the right-hand side. So you try to pile up water on this side. But in the southern hemisphere, you try to pile up the water to your left-hand side. So this here. So the water is going to form like a, they kind of try to pile up in the center. So that's how it developed. And in the equator, the Kelvin wave propagates look like this. So it's like this. In usual case, if there's boundary, the Kelvin wave propagates like this. And right now, they kind of propagates like this. So they create a very like they're going along this direction, but they kind of create a big amplitude at the equator. And that is due to the rotation of the Earth. Yeah, it's kind of hard to digest, but just let you know, the rotation of the Earth can also play a role on waves, especially in big scales. And we'll talk one more case about waves. That's called Rossby waves. The Rossby waves also related to this rotation of the Earth. So this is more easy to explain from atmosphere, but it also happens in the ocean as well. In the atmosphere, we sometimes see this jet streams have this very weird shape, kind of it's supposed to like circle the polar region like this, but when it starts to flow, it's not flowing like circularly. It's kind of bouncing between low latitude and high latitude, and this very weird shape. And the reason for that is due to the rotation of the Earth. And we'll explain that. So think about, so this is an Earth, and Earth is rotating in this direction. So self-rotation in this direction. And if you are in the equator, it's all right, there's no spin. Okay, so the equator, you are kind of doing this. So there's no spin. But when you move up to high latitude, let's say if it's in like the polar region, and you are stand at the polar region, then there will be spin because you are the Earth is rotating and you develop a lot of spins. And there at like mid latitude, you have some spin, but not as high as like the polar region. So the Rossby wave is caused by the conservation of vorticity. We haven't defined the vorticity yet. Okay, so the planetary vorticity is defined by the same as like the Coriolis frequency. So it's depends on the latitude. Also, so this is constant. This is the rotation of the Earth. This is called a planetary vorticity. And the total vorticity have two parts. One part is depends on where you are. That's a planetary vorticity. If you are at the polar region, you will have larger planetary vorticity. Theta here is 90 degree, and the whole planetary vorticity to omega. So, but if you are in the equator, you got 0 planetary vorticity because you don't have any spin here. So that's for the planetary vorticity, depends on where you are. And the water itself can also spin, not because of the Earth spin, but because of maybe I stirred it this way, or there are some motion that caused it to spin. So the total or the absolute vorticity have two parts. One part depends on where you are. The other part depends on, okay, the spin, how spinning you are. So that relative vorticity is is defined as this zeta, this curve and the current, horizontal currents. This, if you remember, if this equals to 0, we have the irrotational flow. And sometimes the flow can be rotational when this curve is not 0. So that is defined the relative vorticity. Okay, so the total vorticity has two parts. And one is the way it depends on where you are. The other part is how fast you spin. And the Rossby waves developed due to the conservation of the total vorticity. So no matter how you move, the total vorticity has to conserved. So let me see. Okay, I have this figure. Conservation of total vorticity. Okay, think about if the flow at the beginning try to like circulate at this latitude, and somehow the Coriolis, when it travels, Coriolis force try to defeat it to the right? So it will kind of go to the higher latitude. I don't know why, but somehow it kind of, let's say if it sometimes flow to the high latitude, what will happen? For high latitude, you will got like much more spin. And you have to control that. Okay, so this is our total vorticity. And if you go to the higher latitude, it's kind of, how to explain this? I have trouble explaining this now. Okay, let's do it again. So this is the total vorticity has to conserve. It has two parts. One part is the planetary vorticity, and the other part is the yourself, how spin yourself. So if this part increase, your spin has to decrease. And if the planetary vorticity decrease, you have to increase. So this is kind of the conservation work. One part goes bigger, the other have to go small. So similarly, if say here, along here, there's no spin, if go to higher latitude, it will start to develop spin, and the spin will along this direction. And that spin will bring the water back to low latitude. However, the water didn't stop, it keep going and go to lower latitude. And to conserve, you have to circulate to the other direction. And that different circulation will bring up the water back to like high latitude, and back and forth. So eventually it develops some shape like this. So it's not circulating around, it's kind of go to low latitude, high latitude, low latitude, high latitude, it kind of bouncing back and forth. And this is due to the conservation of vorticity. This is for the air, but in the ocean we have the similar concept, but it's not easy to illustrate from satellite. Okay, I think for now we covered all the waves. I didn't cover the capillary waves. We only talk about a little bit about when we talk about the surface tension. But this is kind of a summary for all the wave types. And capillary waves, due to the restoring force, is the surface tension. And gravity wave, of course, their restoring force is the gravity. And internal wave is also restoring force is also the gravity. But internal wave in stratified ocean, the Coriolis force, the rotation of the Earth, can also play a role. So it can have two components. And the cavern wave, the gravity is important, but also the rotation of the Earth is also important. Finally, the Rossby wave, the restoring force, they call it beta effect. The beta here is defined as partial F, partial Y. So it's the kind of the how the F change along the Y, the latitude. So that's called the beta effect. And from that, they already figure out the dispersion relationship for all of them. For instance, we are very familiar with this the dispersion relationship for gravity waves, shallow water and deep water. And the cavern wave is very similar to shallow water, but with some rotation. So this is just kind of a summary, but I'm not going to go into the detail for that. Okay, I think I will stop it for now. That's it for today's class.